Exciting. Exciting stuff. Okay. Next question that we got on the menu today is how do we convert wavelength to energy? There, it's kind of a little bit of an improper way to ask the question. A better way to ask the question is, given a wavelength, or find the energy associated with the wavelength of electromagnetic radiation. Okay, now we got to specify electromagnetic radiation because, like, convert wavelength to energy. Are we talking about water waves? Are we surfing and we're going to convert those wavelengths? We can't use the same equation for that. We got to specify that we're talking specifically about electromagnetic radiation when we use this equation. Okay, and the wavelength is a property of a wave. So you can't just convert wavelength without knowing like the other properties. So you do need to know like what type of wave it's in and what context are we going to be using it in. Now the equation that we want to use for here is energy equals hc over lambda. Lambda is a Greek letter. A lot of physics and math we use Greek letters because the Greeks were pretty good at science. So this is energy. E for energy makes sense to me. Lambda is wavelength. The h, that's Planck's constant. And c is speed of light. Now, h, the value of h is equal to 6.626 times 10 to the negative 34. And c is equal to 3.0 times 10 to the positive 8. The units for here is joules seconds, joules times seconds, and for speed of light, it's meters per second. Planck, that was a very smart scientist. He works a lot in like quantum physics. A lot of things in science are named after him. Like the smallest possible unit of time, and the smallest possible unit of length. They're all called like the Planck meter, the Planck second, or Planck distance. Yeah, fascinating stuff. But anyways, if we're given the wavelength, wavelength will be given in meters or given as a length. Generally meters. And energy is going to be joules. Okay, so let's run it through an example. Okay, so suppose that we have wavelength that is equal to 500 nanometers. I think that could be like a laser pointer because I remember I was doing an experiment back in high school, and we calculated the wavelength of a laser to be like 500 nanometers or something. So let's do the math and figure out how much energy it would have. So 6.626 times 10 to the negative 34 joules per joule seconds multiplied by 3.0 times 10 to the 8 meters per second. The seconds down here in meters per second neutralizes the joule seconds up here. And this whole thing divided by 500 times 10 to the negative 9 meters. The nanometers, the nano in nanometers, you can convert that nano into a multiplication of 10 to the power of negative 9. I would strongly recommend that you do that every time you get like a more complicated unit. or like a compound or a unit with a prefix. Okay, so the meters up here neutralizes the meters down here, so all that's left is joules, which is very appropriate for measuring energy. So our units check out, so we just got to math it out, and then we can celebrate the fact that we are so good at physics. So 6.626 times 10 to the power of negative 34. That's a very small number. Probably smaller than 1. A lot smaller than 1. Yeah. Okay, times 10 to the power of negative 10 to the power of 8 divided by 500 multiplied by 10 to the power of negative 9. Cool. And the result of that energy is not very big, but it's still there. So that energy is 3.975 times 10 to the negative 19 joules. Not very much, but more than 0. And sometimes just being more than 0 can really make a difference. Yeah. Okay, so yeah, this solution is good, and yeah, I guess with the universal wave equation that does work out. So yeah, the above solution is good. However, F is more commonly used to represent frequency. V can be confused for velocity or voltage. Cool.